Hello, everyone, and welcome to Season 2. In Season 2, we are going to be transitioning from the sums of Season 1 into the integral, which we've mentioned is the point of Calculus 2, the integral being related to the sums, as we talked about in Episode 1, that integrals are basically sums where you have a lot of data to work with and very little space between your data in the table. Today we're going to be talking about what that means in more concrete, more formal terms, more sort of careful terms. And to that end, we have our objectives for today. We're going to describe what's called the definite integral of a function as a limit of a Riemann sum. We are going to be talking about the relationship between an integral and the graph of a function, and we're also going to be exploring some symbolic notation and terminology for integrals. So, what is the integral? When someone talks about an integral, or sometimes you will also hear the term definite integral, what they are talking about is a Riemann sum where the delta x has become extremely small, extremely small, where the space between your data, the space between your x's for your Riemann sum is very small. Now, put another way, you could also say that a definite integral is a Riemann sum where the value of n, the number of chunks, the number of subdivisions, has become extremely large. These are just two different ways of saying the same thing. A Riemann sum with very little space between the data, a Riemann sum with an extremely large amount of data. That is a definite integral. Now, if you wanted to be very careful and formal, then the Riemann sum could be understood using limits. If you wanted to do a formal definition of a definite integral, I would say that the definite integral of a function can be obtained by taking the Riemann sum and then taking a limit of that value as delta x gets very small, a limit of that Riemann sum as delta x gets very close to 0. That would be the formal symbolic way of saying what we've said in words up here. Delta x becoming very small for your Riemann sum and the data points getting very close together. Alternatively, you could say that it's the limit as n approaches infinity of your Riemann sum. This would just be another way of saying that your n has become very large. What we said in words up here is the same as these symbols down here, the limit as n approaches infinity of your Riemann sum. Two different ways, ultimately four different ways, of saying the exact same thing and capturing the same idea. An integral is just a sum with a heck of a lot of data. Now, this definite integral has some symbolic notation that is used to represent it. Again, symbolic notation is there as a nice, convenient, compact shorthand for mathematical quantities. And the symbolic notation that you'll use for a definite integral is given by something that looks a lot like what you have up here. So the first sort of big feature of the integral is this integral symbol up here. It's like a very long S. That S is for sum. It's long, I guess, because it represents the sort of stretched out case, the sort of extreme case of the integral, long S. Now, this value at the bottom, A, is being used in the same way that we used it when we did Riemann sums. This is the smallest x value in the interval that you are working with. And that B is the value of x on the other side of the interval for your Riemann sum. B is the largest x. Then in the middle, you have the function f of x, for your Riemann sum. And then this symbol dx over here to the side, this symbol dx can be thought of a couple of different ways. Grammatically, the dx closes the interval. The dx is also sort of what becomes of this delta x as it gets very small. So that dx is basically standing in for a very, very, very tiny, a very, very, very small delta x. Now, when we talk about integrals, there are a couple of words that are used to refer to the different pieces of this integral, and I would like you to be familiar with those as well, because that's part of our communication knowledge. In this context, the A and the B are called the limits of the integral, not to be confused with these limits up here, mainly talking about limits like this is the outer edge, the outer limit of the x's that you're working with, and this b is the sort of outer edge or the outer limit of the x's that you're working with in your interval. Specifically, a here is called the lower limit. B here is called the upper limit of the integral, or the upper limit of your x's, put another way. Additionally, we have a name for this quantity on the inside of the integral. This quantity on the inside, this function that you are taking the integral of, this is called the integrand. The function that you are taking the integral of, the function that is a part of your integral, this function in the inside, this is the integrand. Additionally, when you see this integral set up, this dx on the outside, specifically this variable that's being used here, x, is sometimes being referred to as the dummy variable. Dummy variable because in your final answer, x will not be in the final answer anymore. So in situations like this, even though x shows up in the problem statement, you should not expect to get an x in your answer most of the time with a setup like this. So I think that's why it's called the dummy variable, because it shows up in the problem, but it doesn't actually show up in the answer at all. So terminology and symbolic notation for integrals, the upper and lower limits, the integrand, and the dummy variable, x. Symbolically here, in words here, you will need to know all of that information because that's part of our communication knowledge. Now we've talked about the relationship between the Riemann sum and the net area between a function and the x-axis. And so if integrals are connected to Riemann sums and Riemann sums are connected to graphs, then it must be true that integrals are connected to graphs. So let's explore a little bit about what that connection looks like between integrals and graphs of functions. So talking about Riemann sums, we noted that Riemann sums give you an estimate for the net area between a graph and the x-axis, because the delta x in the Riemann sum formula was the width of a rectangle, and the f of xi star was the height of a rectangle. You multiply those together, you get the area of a rectangle, and then the formula adds together many areas of many rectangles, and you get an estimate for the net area between the function and the x-axis. Now, I think this image off Wikipedia does a really good job of showing visually that there is a relationship between the width of your rectangle and the accuracy of your estimate. If you have rectangles with really large width, really big delta x, really small n, then you're getting rectangles that are often very far away from the graph of the function. And so you're getting huge mismatches between the area of the rectangles and the area under the graph. There are these huge gaps missing. There are these big overlaps. So this is a big problem. However, if you make your rectangles a little bit less wide, if you start to shrink the width, shrink the value of delta x, then we can see right away that these sort of narrow rectangles are holding a lot closer to the graph of the function. And as you shrink delta x even more, and you shrink delta x even more, we can see that the gaps between the rectangles and the graph of the function have started to become very, very small indeed. The smaller delta x becomes, the better the Riemann sum estimate becomes for the net area between the function and the x-axis. Now, if you take that idea to its extreme, and you let delta x become extremely small, if you let it approach zero, like in a limit, then as delta x becomes smaller and smaller and smaller, all of these errors begin to shrink, and eventually the error completely goes away. As delta x gets smaller and smaller and smaller, what used to be an estimate now becomes perfect. And as a result, we can conclude that the definite integral of a function from a to b is no longer an estimate, but is actually equal to. It has now become a perfect calculation. It is equal to no error, the net area between the graph of f of x and the x-axis. The Riemann sum estimated that net area. The estimate was bad if delta x was large. However, the estimate becomes better when delta x becomes small, and when delta x becomes very, very, very small, that estimate becomes perfect, and as a result, your definite integral is a perfect calculation of the net area between your function and the x-axis. Let's explore this idea in the following exercise. In the following exercise, we have been given a definite integral, the integral from 0 at the bottom to pi at the top. Our lower limit, in other words, is 0. Our upper limit is pi. And our integrand, the function in the middle, is sine of x. So the question is, graphically speaking, what is represented by this definite integral given symbolically? Well, based on what we observed right up here, the definite integral graphically can be thought of as a net area. So in this case, this integral would specifically be the net area between the graph of sine of x and the x-axis. On what interval? On the interval of x's from 0 at the bottom, that's our lowest x value, that's our lower limit, to pi at the top, that's our largest x value, that's our upper limit. I could ask a similar question about this definite integral. Almost the same, but only one thing has changed. This time our lower limit is not 0. This time our lower limit has been changed to negative pi. So someone says, what is graphically represented by the expression the integral from negative pi to pi of sine of x? Once again, I could say that this is net area. Graphically, this is exactly equal to the net area between sine x and the x-axis. On what interval? On the interval as x's are going from minus pi at the bottom to pi at the top. Now, if you keep this principle in mind, if you keep this graphical significance in mind, then you can actually calculate certain definite integrals with barely any effort at all. As a matter of fact, I think that we can actually calculate the exact value of this definite integral right here using this idea. They say, therefore, based on that, what is the value of this definite integral, negative pi to pi of sine of x? Now, bearing in mind that the definite integral represents this net area between the graph of the function and the x-axis, I'm going to get myself over here to Desmos, and I'm going to go ahead and graph sine of x, and I'm going to look at it on the interval from negative pi to pi, and I'm going to see if anything stands out to me as interesting. Now, net area gives me a negative area for regions below the x-axis, and it gives me a positive area for regions above the x-axis. Bearing that in mind and looking at this picture, what do you think is the value of the net area? Well, the net area is a combination of the positive part and the negative part, allowing the two to cancel each other out. And because of the symmetry of the function sine of x, because of the symmetry of this image, we can see that this region above the x-axis is basically exactly the same as this region below the x-axis. The only thing that's different is that one is on top and one is on the bottom. So when they are combined, the positive area and the negative area will cancel perfectly because of that symmetry. The net area between this function and the x-axis on negative pi to pi is exactly equal to 0. And because the net area is exactly equal to 0, and the net area is exactly equal to the integral, it must be true that the integral's value is also exactly equal to 0. This exercise, this example that we've done right now is really, really, really important. This idea of using symmetry and using geometry to calculate integrals really, really quickly is going to come up very often in this class. Okay, temporarily moving on from the graphical significance of the integral, I want to talk about the real-world applications of the integral. In season 1, we saw that the Riemann sum had many, many, many physical applications, many physical quantities that the Riemann sum was used to find, and therefore, because there is a connection between Riemann sums and integrals, we should also be able to use integrals to find physical quantities. So let's explore that. Say, for example, that I'm back in a season 1 scenario, and I have a function p of t, which describes the speed of an object at a time t. If p of t represents speed and t represents time, what physical quantity would be estimated by a sum like this one, a Riemann sum involving a product of speed and time? Well, we saw back in our very first episode that if p of some input represents speed or a rate, and delta t represents a length of time, then the product of those would represent a distance traveled over that length of time. And if I took a sum of those products, a sum of rates times times, then this would give me a total distance traveled. We noted in our very first episode that this result of this sum would just be an estimate for the total distance traveled, because this assumes that the speed of the object is constant in between our data points. However, we observed in that first episode that as we collect more and more data and our data points get closer and closer together, in other words, as delta t approaches 0, as that Riemann sum transforms into an integral, that Riemann sum goes from estimating the distance traveled to calculating the distance traveled. What physical quantity would be calculated by this integral of speed with respect to time, p of t dt? This would also be a calculation, a perfect calculation of distance traveled. Back in episode number 1 of season 1, we explored this idea that if you have the density of an object, if you have the density function for an object, then products of the form density times length give you the mass of your object. And if I sum all of those together, then I'm getting the total mass of my object. However, we noted in that first episode that if you do that via a Riemann sum, this is just going to be an estimate. That estimate is going to get better and better, however, as the number of data points that you have gets larger and larger, and the space and the gaps between your information get smaller and smaller. And so, as delta x gets smaller and your sum transforms into an integral, you're still going to be calculating total mass, but the difference is that this calculation is going to be perfect. It's not going to be an estimate anymore. It's actually going to be truly equal to the actual mass of the object. Similarly, season 1, episode 2, we were talking about cross-sectional area. If you have a function that tells you about cross-sectional area and you multiply it by delta x, if you take area and multiply it by length, then you get from that volume. And if you sum together a bunch of areas times lengths, then you get the total volume of your object, but again, this is just an estimate. It's just an estimate. But as you collect more data, and as the gaps between your data get smaller and smaller, then that estimate begins to become perfect. And as that delta x gets smaller and that Riemann sum becomes an integral, then you're still calculating total volume. But this time there's no error anymore. It's not an estimate anymore. It's perfect. It's a perfect calculation. So that, in my opinion, would be my major takeaway from this part of the discussion. The major part of this discussion is that integrals can do all the same things that Riemann sums can do. The major difference is that Riemann sums can only estimate the answer, whereas integrals can perfectly calculate the answer, perfectly. However, this doesn't mean that the definite integral is the best tool for every job. The definite integral at the moment has one major downside to it. One major downside. And the major downside to the integral at the moment is that we don't actually know how to find it, right? The only problem in today's episode where we were actually able to calculate the definite integral is in this special one that we had right here, where we were able to calculate the integral using a graph. But besides this one example, we actually haven't talked about how to find integrals yet at all. So that, I would say, is the major advantage of the Riemann sum, is that the Riemann sum is something that we actually know how to calculate and can calculate just using the basic principles of algebra, arithmetic, and pre-calculus. We're going to have to develop additional tools to help us to calculate definite integrals and get these perfect results here. So that concludes today's video. Today we introduce the concept of a definite integral, formally and officially. And once again, we said an integral is just a Riemann sum where the space between your data points, the space between your entries in the table, the width of your rectangles, your delta x, these have become very, very small. They're approaching zero. The major difference between a Riemann sum and an integral is that Riemann sums estimate while definite integrals calculate perfectly. Riemann sums estimate net area, integrals calculate net area. Riemann sums estimate mass, distance traveled, and volume, whereas integrals calculate mass, distance traveled, and volume.